Good, then let's continue and finally talk about the p-values. So remember again that p-values in classical statistics always relate to probabilities under the null hypothesis. Yeah, so the whole random field theory based stuff that we've discussed so far all establishes a null model, and the important thing is, of course, that we make this assumption of a stationary random field which has an expected value of 0 everywhere. Yeah, and based on that, we are now looking at a number of probabilities that relate to the definitions that we just made and the random variable c larger than ku. And the first thing we can talk about are the set level inference p-values. Well, there's actually only one p-value, set level inference. So that's in the very left of the SPM table. And yeah, this is what we're talking about now. And here we assume that we are interested in the following probability: the probability that the random variable c for the volume defined by the cluster extent threshold that we just defined and the cluster forming threshold u that we've just defined is larger or equal to the number of observed clusters. Yeah, so it's fairly important that you are fluent in kind of interpreting these kind of statements. So I always wrote them below again. So this is the probability that for the specified cluster forming threshold tilde u, yeah, this is tilde u, the number of clusters within the excursion set E tilde u that have a volume equal to or larger than the specified cluster extent threshold value k, this one, is equal to or larger than the observed number of clusters C tilde. Yeah. So in this expression, the cluster defining threshold that you enter plays a role, the cluster extent threshold that you define plays a role, and the number of observed clusters plays a role. Yeah. So it's the question is, under the null hypothesis, how probable is it to see as many clusters as you have observed or more, like always in kind of this p-value logic? So what is the probability to see as many clusters as you have observed under the null hypothesis, as many as you have observed or more, given values of the cluster forming threshold u as you have defined and cluster extent threshold or of a volume equal to or larger than k as you have defined. Yeah, that means if you set the cluster forming threshold higher and higher to see more or less clusters as you have more or equal to clusters as you have defined gets more unlikely. If you increase the volume threshold, this gets more unlikely. But yeah, so this is what this set level inference relates to this p-value, and how it's actually evaluated under SPM is as follows. So the probability to see as many as you have observed or more is 1 minus the probability to see less than you have observed. So this is now more on the implementation than on the logic of what this relates to. So and this can be evaluated as 1 minus the Poisson cumulative mass function, and this is how it's done. This is why I'm doing this for And there's a typo in the script. It needs to be tilde c minus 1, because otherwise it will include c, and it needs tilde c, and it needs to be smaller than. So if you go into the code, and you will be able to go into the code, I mean, you're already able to go into the code. So if you look into the SPM p rf function, you see that things are passed into the Poisson cumulative mass function, and what is passed there is actually the number of observed clusters minus 1 for the cluster extent threshold that you defined, and the cluster defining threshold u that you also defined. Yeah. So this just evaluates under the null hypothesis how likely it is to see as many clusters or more that you have observed for a given cluster extent threshold that you decide, and a cluster forming threshold that you decide. Yeah? Why these set level inferences? So they are there, I think, maybe mainly for the reason that Friston et al. In 1996 realized that this would be a generalization of what had been done previously, namely at the cluster level and at the peak level, as we will also see in a second. Why the reason why nobody actually uses them that much is because they are, of course, fairly anatomically unspecific. It just talks about the number of clusters in this excursion set, but it doesn't say where these clusters are located. Or so the rhetoric is then always that it doesn't have localizing power. But this is, I go crazy when I hear these kind of things, because it's completely unclear what localizing power should mean, and it just suggests something like power in a statistical sense. It's completely lost. So what the important thing is, this is under the null hypothesis, the probability to see as many clusters as you have observed or more for a given cluster defining threshold and a cluster extent threshold. Yeah. So if you change the cluster extent threshold, like I said in the beginning, this p-value will change. But then, because nobody's interested in these set-level inference p-values anyway, this is rarely a problem. Yeah. So that's what this set level is. And I mean, it's informative. So in the sense, well, I don't know in what sense actually. I mean, so the thing, of course, you always should interpret p-values as surprises. Yeah. So in the sense that under the null hypothesis, to observe what you just have observed, that there are like 10 clusters that are of volume larger than 80 voxels at a cluster defining threshold of 4. That's really surprising. So that happens so rarely under the null hypothesis. So it must mean something. This is how you should interpret this, right? This is p-value logic. And if you want to, if you find, for example, like 10 clusters which are fairly big, then you can tell your reader under the null hypothesis to see this. If, for example, this p-value is, I don't know, smaller than 0.07, or let's say it's 0.07, that's what it is, then you say, that's fairly unlikely, dear reader. Yeah, good. So they are there because they realize it's a generalization, but I think people don't use them that much. This is completely different for the cluster level inference p-values, because everybody loves them. Because the cluster level inference corrected p-values get significant quite easily. So people love to report them, including myself, because you have something significant. You've done a good job. If it's not significant, you did a bad job. If it's significant, you did a good job. So we're now first talking about the so first about the family-wise corrected cluster level p-value. So assume now the following. We are interested in this probability. The probability, again, of our c larger than ku random variable, but now for the cluster volume tilde ki, our cluster defining threshold u, and for this to be larger than 1. Yeah? So now the very important thing is that we are talking about the observed cluster volume for cluster I. Yeah? So that's volume of cluster I, where I goes from 1 to the observed number of clusters. Yeah. So this tilde ki, this is also reported in the SPM table. So this is this, if you look into the cluster level column, there's this ke. The ke, especially the e, I think relates to equivalent, because what is printed into that column is the number of voxels in this cluster. So there's, for example, in the first cluster that you see here, there are 1,176 voxels. You of course know by now that volumes in random field theory-based p-value correction are measured in results / Lebesgue measure, but really in this case, of course, in results, because we take smoothness into account. So this is why this is called the equivalent, because this is results converted to voxels. There is a conversion factor. Actually, I have this other table in the printout, in the handout, sorry, where you see in table 7.1 now what we've already talked about, so the set level p-value, and then you see in ke, you see how it's converted. So it's essentially converted by this conversion factor corresponding to the full width half maxima, which is the same thing as, if you remember, how Lebesgue measure was converted into Riesel volume in the volumetrics. Yeah. Maybe that we look at this table. So you, for the set level, I forgot to tell you that this C is the number of observed clusters. Yeah. So if you now look again into the real SPM table, you see that at the set level, we talked about the p-value. You see that there are 6 clusters. And now we're talking about the volume of the first cluster, which in voxels is, in units of voxels, is 1,176. And this would be here k tilde 1. Yeah? So we're talking now about the probability of observing one or more clusters of volume equal to or larger than the volume of this specific cluster at a specific cluster defining threshold. So what you already see here is, of course, that the cluster extend threshold, this k tilde, doesn't play a role. It's not there. Yeah? I mean, it plays an implicit role that if you would have set your cluster defining threshold at, let's say, 2,000 voxels, then this cluster wouldn't be there anymore, and then you wouldn't be able to talk about it. But once a given cluster volume is larger than this cluster extend threshold, the cluster extend threshold doesn't play into this p-value anymore, because it's relates to the volume of the specific cluster. Yeah. So the question that is answered here, or that is asked and answered, is what is the probability to see one or more clusters of a size as large as the cluster you're currently interested in at the cluster defining threshold that you're currently interested in. And this one or more, this is what we will see next time, is closely related to the idea of family-wise error correction. So this is why this one or more is interesting. But we don't worry about this. Once we know what family-wise error correction is and why this relates to this one or more, we will come back to this p-value and then basically clarify why it's listed under PFWE corrected. But this whole PFWE corrected is irrespective of the fact that what is, or it doesn't influence the fact what is printed there is this probability. Yeah? Why it's interpreted like a corrected p-value we will discuss later. So then the question is, how is this evaluated? This is evaluated as follows, and this is again what you find in the 1996 Frist and al. paper. So the probability to observing more or one or more clusters of the volume of this particular cluster you're interested in and the cluster extent threshold, the cluster forming threshold is 1 minus the probability that this is smaller than 1. Yeah, so this is just the reverse probability, so equal or larger than 1 versus, or the complementary probability versus smaller than 1. Smaller than 1 in this case, especially if it's a Poisson distribution, which is defined on the integers from 0 to infinity, so 0, 1, 1, 2, 3, and so on, corresponds to the cumulative Poisson mass function for 0, yeah, which is, of course, I just put this in here. So if you think that the cumulative, we can go, actually, we have that here. This sums from j to 0 to the c that you put in. Now you put in 0, so it's just the probability that the number of clusters with a volume larger than the volume of the cluster you're talking about is 0, and this is, of course, then the same thing. There you have to think about this. If x is 0, what is lambda to the power of x? Yeah. And what's the factorial of 0? 1, exactly. So the only thing that remains is the exponential of minus lambda. And this because lambda in this case, so our lambda c larger ku is, as we discussed, ECU P ku larger than k, then corresponds to 1 minus E C tilde U P K tilde U larger than K I. And this expression here, this expression is the same as the expression for the maximal cluster volume, which we haven't actually discussed last time. I now put into your script with an explanation. But because we will come back to this anyway, because we have to clarify how this relates to the idea of family-wise error correction at the cluster level, I will again not discuss it at this point, and we will come back to it, so we will see it again. But it's fairly straightforward to see that this special case of the number of clusters larger than, there's a tilde missing, larger than with a volume larger than KE at the cluster defining threshold, smaller than 1, is essentially the same, no, not essentially, but it is the same as the distribution of the maximum volume. We will come back to that and make that more clear, because it really relates to this family-wise error correction. But again, this the important thing is that this is what is printed into the SPM table. Yeah, so this is what is reported as the family-wise error corrected p-value at the cluster level for the clusters I, 1, 2, C. And then the uncorrected p-value that you also find there is actually the following. So this is just the probability of observing a volume of clusters larger or equal to Ki tilde, so the volume of this under the null hypothesis. Yeah. So mind the difference. So this is the probability of seeing a volume larger or equal to Ki, and this is the probability of observing one or more clusters of a volume larger or equal to Ki at this threshold. So again, I put this into the table, and what we of course need to talk a little bit more about is why one of them is interpreted as this family-wise error corrected one, but regardless, it is this probability that is reported there. Good. And then finally, we can talk about the peak level. Questions right now? No. So now assume that we are still interested in our probability of this C larger than KU random variable, but now for the following: C larger or equal to 0 and a cluster defining threshold not, and this is very important, not equal to the cluster defining threshold that we selected when we set up this SPM table, but a hypothetical cluster forming threshold defined by the maximum of our cluster. So that's our T tilde I. We're interested in the probability that the number of clusters with a volume equal or larger than 0 at a cluster defining threshold corresponding to the maximum of our cluster is larger or equal to 1. So that's what is reported as the peak level family-wise error corrected p-value, and why this is, one can also explain, as I will in a second. The important thing is that, of course, these p-values don't directly depend on the cluster forming threshold that you enter in the very beginning, because instead of having tilde u here, you have the maximum. So this is not doesn't play a role, and also here the cluster extent threshold doesn't play a role. Of course, indirectly they play a role, because if you set them too high, you will not observe this cluster, and the whole thing will not be evaluated. How is this evaluated, and what does it relate to? Well, it's the following. Again, with the logic that larger or equal to 1 corresponds to one minus the same thing smaller than 1, which is again, like we've just seen, the cumulative mass function of the Poisson distribution evaluated at 0, which we've also seen previously is then c larger than 0 tilde I equals 0. And now again, of course, this corresponds to 1 minus x of the expectation to see the expectation of the number of clusters to see at a threshold that is given by the maximum of our current cluster. So, for example, if you look at the first cluster, which had this, to make this explicit, the first cluster had a maximum of a t-value of 15.7 or something, 15.70. Now this is what I'm just writing up here is the expected number of clusters under the null hypothesis at this threshold of, in this case, 15.7 times the probability that k tilde I is larger or equal to 0. Now you might remember or not that this probability k tilde I larger than something was given by an exponential, so that was this minus beta times c, or whatever this thing is, which was is this number. So this is an exponential, and here in this case you put in 0. So the exponential of 0 is of course 1. So this thing evaluates to 1, which is kind of, that one has to think a little bit from a philosophical point of view, that the probability, if you see any cluster, that this has a probability larger or equal to 0 is, of course, 1. But this is all basically on the assumption that you actually, well, this is again this question, if you don't, if you have a high threshold, you can, clusters of size 0, of course, have a probability 1 because they are not there at all. That's the thing. It makes, from the math, it makes sense. If you think about it, it gets a little more tricky, but the math is simple. So you get 1 minus x minus the expected value of the number of clusters at the threshold given by the given by the maximum of this cluster. Now this, somewhat surprisingly, actually relates to something that is at the very origin of the whole random field theory based p-value correction business, namely the probability that the maximum of the statistical field is larger or equal to ti. So the probability that we've just evaluated here, that the number of clusters at this hypothetical cluster forming threshold of ti with volume larger than or equal to 0 is larger or equal to 1 is approximately the same as the probability that the maximum of the statistical field, which we called xm, is larger or equal to tilde I, which is somewhat surprising, and we will look at that in a second. This is also relates fairly close to why this is interpreted as a family-wise error-corrected p-value, because this relates closely to the maximum statistics. So the question is, what is the probability that one or more over all of this whole thing happens, which is the same as that the maximum is larger than something. We have to talk a little bit more in detail about this. So this relationship basically gets the old idea of looking at the maximum into this framework of the Poisson distribution for this random variable C Ku. Now, why is this approximately the same? This is due to the fact that actually 1 minus exp minus the expected value of C tilde I is approximately the same as the expected value of C tilde I. Yeah, so that this expression here, 1 minus the exponential of minus x, is approximately the same as x itself. And the expected number of clusters at a given threshold, you know that this was approximated by the Euler characteristic for the excursion set defined by this, the Euler characteristic of the excursion set given by this cluster forming threshold, and we discussed that this is what is used as the probability for the maximum to exceed a given hypothetical threshold. So the whole magic in this approximation is actually in this approximation here. And the question then is, how good is this approximation? So what this approximation actually says is that 1 minus Ex is approximately x, which is something one can think about. Why this might be the case. And this is what I looked into a little bit in this proof of 7.10. So this relates to the series definition of the exponential function. So you either know or you don't know that the exponential function, or you kind of know that the exponential function is defined as a series, so an infinite sum. So exponential of x, e to the power of x, is defined as the infinite sum over these terms. So factorial of I as dividing x to I, so this dependency of x is in this x. So that's how you evaluate Ex. And if you think of the first two terms, this is of course x0 factorial 0 plus x1 divided by 1 plus the remaining terms, and there are many because you go from 2 to infinity. But if you now say, for the sake of the argument, that okay, this is, as we've just seen, that's 1, and this is x, and you say, oh, whatever, I'm a physicist, I don't care about things that are, so this is a typical physicist thing, so to basically so do Taylor expansions and stop things after like 2 or 3 terms. There's a joke about this. So the mathematicians, they care about the whole thing, then physicists, they care about until here, and engineers, they basically stop here or something. There's a kind of a joke which also always makes you worried when you board a plane. But that's a different story. So this relates to, this then says that E is approximately 1 plus x. And then you can do the same thing as you do with equations. So you get the x on the other side, and you get the ex on the other side, and then you replace x by minus x. So you have minus this 1e minus x, and then you have x being approximately 1 minus e to minus x. Actually, I looked at that. That only really works for fairly small values of x, so that it looks good. But seems to be good enough. And so this thing here is what is printed into the SPM table under the corrected peak level inference. And this is how it's interpreted, that the probability for the maximum to exceed the cluster forming threshold defined by your t-value of your current cluster. So this is now the peak level PFWE corrected, and the t-value, as you also see in my new table. So that's the peak level PFW. And then what is left is the uncorrected p-value at the peak level. And what this actually is, so the uncorrected one, this is the uncorrected peak level p-value is actually the same thing. So that's again the probability of the number of clusters at a cluster defining threshold given by the maximum of the cluster that have a value, the volume larger or equal to 0 is larger than 1. That's the same thing, but under the assumption that the Riese volumes are all 1. So you know that the Riese volumes take into account the actual search space. So if it's bigger, the Riese volume gets bigger, and they take into account the smoothness. If it's less smooth, the Riese volumes get bigger. I hope I'm not saying this the wrong way around again. So they actually account for the fact that you have kind of this multiple testing problem in the sense that you have a big search space, and they account for the fact that how these p-values come out under the null hypothesis depends on the smoothness. Remember that if things are not smooth, so if you have something like this, then that you get something larger than some threshold u is more likely as if you have something that is smooth. Now for the uncorrected p-value at the peak level, this dependency on the search space, on S, and on smoothness, on the full width half maximum, this is I think annihilated is a good word. So this is taking out of the considerations, and it's just said, okay, the volume that we're interested in and the smoothness is just 1, so it doesn't have an effect. And then this evaluates just to the expected Euler characteristic under this assumption about the Riese volumes, which then just evaluates to the Euler densities, because the Riese volumes don't factor in, or they factor in with a value of 1. So this is what is printed into the uncorrected p-value at the peak level, which is not really evident from the labels in the table, I would say. But if you go into the code, this is what's actually being done. Yeah. So I put all of these things into the table 7.1, which gives the expression under the theoretical framework that we have revised for these different things. And what is left to do then is to understand why this things like a probability equal or larger than 1, why this can interpret it from the perspective of family-wise error correction, but keep these separate, right? So one thing is what is in there, and the other thing is how it's interpreted. And what is also left to do, essentially, for the course is to talk about how these result volumes are estimated, and I hope to do these remaining things in the last 3 weeks. Questions about what is printed into the SPM table or something like that? But I hope you see from this little exercise here this morning that, or at least I see it and I feel good, that all this theory that we discussed and all this introduction of random variables and or discussing about what the covariance function of a random field is, this has immense practical implications. So it's not some theory that is like, let's deal with this theory, but practically it doesn't matter if you do an fMRI study and then do a GLM analysis, then you just look into the SPM p-value table and then you know what's going on. Well, you don't know what's going on because it's all related to this quite evolved theory. So I hope you see the practical significance also. If not, God may help you and judge you, but I'm out of the business. Any other questions? Nobody asked a question yet. But no, good. Then, next time, family-wise error correction and why this probability larger than 1 relates to family-wise error correction, and on we go. Yeah, good. Then see you next week, or in 15 minutes, or tomorrow for the lecture. Anyway, goodbye.